Welcome to the 2024 Earth Science Week webinar series celebrating Earth science everywhere. In celebration of Geologic Map Day, which falls on the Friday of Earth Science Week, AGI works with partners to create a Geologic Map Day poster. To highlight this year's theme, Earth Science Everywhere, the 2024 poster features the unified geologic map of the Moon created by two long-standing Earth Science Week partners, the U.S. Geological Survey and NASA. This detailed map can help introduce students to the study of impact craters on the Moon on a global scale. The back of the poster shows close-up images of two moon craters, Tycho and Copernicus, in addition to detailed geologic maps that can be compared to an impact crater on Earth, Meteor Crater. Located in Arizona, Meteor Crater has been extensively studied as an analog to impact craters on the Moon, in addition to being an astronaut training site. Activities for engaging students with this poster can be found on the 2024 Earth Science Week website. Today's presentations relate to the Geologic Map Day poster and discuss how impact craters are studied on Earth and the Moon. Our first presenter, Amber Gullikson, will talk about the history of Cinder Lake crater fields, how they have been used as astronaut training sites, and educational activities produced by the USGS to help students learn about how impact craters are studied.
Hi everyone, my name is Amber Gullikson and I am a geologist with the USGS Astrogeology Science Center located in Flagstaff, Arizona. I'll be talking today about a field guide that will be published soon on the Cinder Lake crater fields, a historic site where Apollo astronauts trained and where work continues for future missions. Cinder Lake, which is located just northeast of Flagstaff, is composed of two man-made crater fields that are one-to-one replicas of two locations on the Moon. The site was used as an operational analog field site where we tested instruments, concept of operations, traverse testing, and much more. We have the guide laid out as follows. However, for the sake of time, I'll focus on what analog sites are and why they're important, landing site selection for Apollo 11, and why Cinder Lake was chosen for this unique site, and lastly, how the crater fields were constructed and their current state. So what exactly are analogs and why are they important to scientists? Analog sites are locations on Earth that represent a similar environment, past or present, compared to another planetary body based on geologic, chemical, or mechanical properties. For example, the image on the right, on the left-hand side is a meteor crater, an impact crater on Earth, and on the right is an impact crater on the Moon. As you can see, there are a number of similar features between these two impact craters. For example, their sharp rim, a similar flat floor, and ejecta blanket located on the exterior portion of the crater. These analog sites can be used to study geologic processes such as impact craters, astrobiology, robotic human mobility, testing new technologies, just to name a few. Using analog sites enables researchers to evaluate instruments and test field methods in realistic environments. They can also expose hazards and limitations that were not previously recognized during the development stage, and the ability to troubleshoot issues on Earth is much safer, easier, and quicker compared to resolving such issues on another planetary body or in space. Additionally, these sites can be great as public engagement efforts, allowing people to see in person what kind of research is being tested before being used in future missions. All the images below are of Cinder Lake, where we see instruments and roving vehicles being tested back in the 1960s. Now stepping back to the 1960s, after President Kennedy proclaimed that we would be the first to land a human on the Moon and bring them back safely before the end of the decade, work was cut out for NASA in determining where the safest place to land on the Moon would be. This image here shows the Apollo zone of interest, where potential landing sites had been narrowed down to these 5 locations, which are located all along the equatorial zone of the near side of the moon. The image below is ideally what they were looking for, which is a site that was relatively smooth and lacked any large craters or mountains. After numerous detailed analyses were completed, Site 2P-6, highlighted by the red box, was selected as the safest location for our astronauts to land. Deciding on this location resulted in its own set of potential issues, such as if you land in an area that lacks any noticeable landmarks, such as large craters or mountains, how do astronauts, once they've landed, locate themselves on a map quickly and accurately? That idea sparked the need to have an operational analog site to train astronauts in field location methods. Now, to determine where that site should be on Earth. Flagstaff, Arizona was already on the map for having other analog sites that were planned as training sites for astronauts. This included Meteor Crater, which is 40 kilometers east of Flagstaff and considered the best preserved impact crater on Earth, as well as the Grand Canyon northeast of Flagstaff that can be used to train astronauts in understanding stratigraphy and superposition. So Cinder Lake, shown here, is just located northeast of downtown Flagstaff and is situated around Flagstaff's landfill. This site was chosen based on its proximity to these other important analog sites and because of its overall flatness, lack of vegetation, and layers of loose basaltic tephra. It was selected to be transformed into a lunar-like crater field. The construction of both crater fields are shown in these images, which consisted of using a backhoe to dig shot holes, and explosives were placed in and later detonated to create the craters. Crater Field 1 was constructed in 1967. The final crater count was 143. Craters ranged in size from 1.5 up to 18 meters in diameter. Here on the left is the completed Crater Field 1 compared to its lunar site on the right. The goal of Crater Field 1 was to replicate one of the selected locations of the preliminary Apollo landing site and implement location testing. That is, how to find yourself quickly and accurately without any obvious landmarks. Other activities were to teach preliminary field methods to astronauts and test instruments. This site, however, was considered relatively simple without much geologic diversity. After Crater Field 1 was completed, the following year in 1968, it was decided to construct a second crater field that would be larger and had a more complex geologic layout that would enable astronauts and other trainees to reflect on stratigraphy, superposition, and other geologic processes. Shown on the left is the completed Crater Field 2, and on the right is its lunar counterpart. The craters range from 2 to 22 meters in diameter, which is about 6 to 70 feet wide. There are 426 craters within this field, and were created using the same explosive materials used in Crater Field 1. The explosions here were used in a more systematic way, however, creating different aged craters. Here I'm just highlighting a couple crater patterns to showcase the spatial precision of these craters to their lunar counterpart. There are a couple more examples of that. So over the past 50 years, both crater fields have experienced erosion to different degrees. This is Crater Field 1. On the lower left is the newly created field in 1967, and on the right is what the area looks like today. The boxes in the upper left denote the location of the top images. When craters first form, they begin with sharp rims, the interior crater walls are steep, and ejecta is visible. On the top left image, the bright rays spanning out from the larger crater is its ejecta. Over time, crater rims become rounded, crater walls begin to erode and fill in the crater, causing them to become shallower, and the ejecta is no longer visible. Here are some images of present-day crater field 1. Sometime after the crater field was constructed, a fence was placed around it, restricting access to foot traffic only. These craters act as excellent basins for rainwater and sea deposition, resulting in many of the craters being inundated by vegetation. In 2019, Cinder Lake and Sunset Crater, the volcano in the background of the lower images on the left, were added to the National Registry of Historic Places because of their role in the Apollo astronaut training program. Just recently, the USGS and Coconino National Forest Service have begun restoration efforts to bring the site back to its near pristine state. Looking at the image taken in 2022, wherever vegetation is seen indicates the presence of a crater. In the restoration efforts, this vegetation is being removed, and on the right, this image was taken just a few weeks ago, showing the effects of this restoration project. Crater Field 2, on the other hand, has become a popular off-highway vehicle, or OHV, recreational site. For many people that use this site, they're pretty enthusiastic that they get to drive in areas where the astronauts used to train. However, this type of recreational activity does not bode well for preserving craters, as you can see in these images here. Additionally, we've had several major fires in the area, which have resulted in flood mitigation control. The map in the center shows the placement of ditches in blue that are directed towards Crater Field 2. When heavy monsoonal storms roll in, this area floods and craters are filled in with sediment. Images along the bottom are a time sequence of the crater fields in 1997 on the left, then in 2013 in the middle after the Schultz fire. The fire shown in the upper left image is of that fire, and again in 2022, which followed several other large fires in the area. Overall, this crater field is experiencing a much greater degree of erosion compared to Crater Field 1 and will eventually no longer be visible. However, at the moment, we can study the differences in this erosion between the two crater fields to better understand crater morphology on other planetary bodies. And lastly, listed here are the activities we have included in the field guide. This is relative age dating activities, learning map scales, field location test, the importance of sun angle, and crater erosion. The video here is an example of part of the sun angle activity, which shows how the look of a crater can change depending on the orientation of the sun, whether it's low on the horizon or high in the sky. My concluding slide is the cover of our field guide, which will be published later this year and available to the public both as a printable PDF version and an online story map. Thank you for all of your time.
Our next presenter, Alex Huff, will discuss geologic mapping techniques used to study impact craters on Earth and how these techniques are applied to the mapping of extraterrestrial impact sites.
Hello, my name is Alex Huff, and I'm excited to talk to you today about learning from Earth to geologically map the solar system. So starting with a refresher, so we're all on the same page, a geologic map is a chart of geologic observations that we use to make interpretations about how a landscape was created and changed over time. So if a geologist went outside and wanted to start making a map, they would walk until they identify an area of consistent rock type. So this geologist is standing in an area of small pebbles that are light white to gray with a few bigger blocks of rock, and we would call this unit A. And then they would continue walking maybe into the background of this photo, where I see areas of pebbles that are dark or black to red and a lot more blocky rocks, and we would call this unit B. And in identifying unit A versus unit B, they would draw that red-orange line contact between those two units where they touch and make an observation about the relative ages they think of each. So in this observation, unit A might be older, shown with an O, and then B would be younger, shown with a Y. And in doing so, this identifies the spatial extent of these units, where we think these rocks are out in the field, and then our history of units. What are the order of events for each unit that we're identifying? And once you repeat this, steps 1 through 3 over the entire field site, you then can create a geologic map as shown on top. So this field site is shown in the red box on the top, where the much larger study site has all of these different colors showing different map units, which mean are different rock types. And all the lines are different types of contacts between these units and linear features like faults or channels. So this geologic map, which was produced in 2023, builds upon a legacy of over 200 years of geologic mapping to perform science. And in doing this, we now have global coverage of many different map scales. So this map here on the left-hand side is at 1 to 24,000, meaning 1 centimeter on the map is 24,000 centimeters out in the field. And this is a pretty standard scale for starting a map site, making a geologic map. But because we've done this over centuries at this point, we have different scales. So this side then in the state of Arizona is that green box in the central west. And this map of the state of Arizona is now 1 to 1 million scale, which means 1 centimeter on this map is 1,000,000 centimeters out in the field. And this state of Arizona map on the geologic map of North American continent is that bright pink box. And this map is at 1 to 5 million scale. So all of these different types of scales and geologic maps demonstrate how we can use them for different science purposes, like identifying natural hazards, locating resources, understanding how global scale plate tectonics have shifted our continents over billions of years. And this has really advanced our understanding of Earth as a planet. But what about other planets? So the space race and the Apollo program really sparked our interest in looking at other planets, specifically starting with the moon. But you can't go outside, or at least at that point when they first started, had astronauts go and look and pick up a rock and see what the rock type is. So how do you start making a map? You start by making observations of imagery, and they specifically use telescope imagery in this Apollo era. So you can start to see darker areas, black, and then much brighter white areas. You can see circles and lines. And these colors and lines are just what you can draw on a map like you would in the field. So focusing on this bright white dot here, this bright spot, white with the gray around it, is Copernicus crater. And Shoemaker and Hackman made the first prototype of a map of the moon of this site using telescope imagery. And so similar to the map I showed previously, all the colors represent different types of map units that the map makers thought were different rock types. And there's linear features everywhere, like crater rims or maybe faults. And this is the first version of what is now known as a planetary geologic map. And planetary geologic maps are data-based geologic maps. You can't go out in the field and verify hand on rock, so it's basically all rooted in different levels and resolutions of data. And what are those? So we first had telescope data, as I showed you on the previous slide of the moon. So these give you kind of hemispheric to global scale observations of the planetary body you're looking at, whether that's a planet or a moon or an asteroid. And then we started to get satellite data. So those instruments, those satellites that are either flying by a planetary body or go into orbit around a planetary body. And they're starting to get slivers of higher resolution data of the body you're looking at, such as Mars on the left-hand side with the temperature of the surface shown in the different colors. Even higher resolution, we started to have landers. So a suite of instruments on a robot that comes and lands, but then is stationary on a planetary surface. And these give us point values of data on a planetary surface, such as Voyager's Phoenix lander's return of ice on Mars. And then lastly, we now have rover data too to add to our suite of data sets. So these are maybe similar different instruments that are then mobile on a rover, and they give you now spatial data points, such as the drill that was on MSL Curiosity. Each of these drills shown on the right was then collected at a red dot. So now we're getting spatial information of this data set from this rover. But you have all this beautiful data. How do you know how to interpret it? You make these observations from data, but what does it even mean when you are looking at a different planet? So to understand these planetary landscapes, we want to start with Earth. You study Earth to understand what a geologic process is and how it proceeds over a landscape and changes. So let's focus on a lava flow, which is a volcanic process on Earth. You would then look on another planet and find similar looking terrains on those planets. For example, I hypothesized lava flow on Mars. And so now that you're looking at Earth versus Mars, you're looking at scale processes, meaning there's a difference between Earth and Mars. And how does that affect the geologic process that you're studying? So Mars is a third the size of Earth, meaning the gravity is a third of the gravity. The gravity on Mars is a third of what you have on Earth. Mars was made up of different type of rock because it accumulated in a different part of the solar system. And it has a different, much thinner atmosphere. And all of this affects how a lava flow would erupt over the surface. So now that you have your hypothesized process and you understand how it scales for the body you're looking at, like Mars, you can start to build a story. And this is combining volcanic processes with wind and water and gravity-driven processes. And this creates, an understanding of a landscape over Mars. So now we have data and we have our understanding of geologic processes from Earth. How do you make a map? And these come down to fundamental principles of database geologic mapping or planetary geologic mapping. And these are kind of established because if you think about an artist who's creating using different types of medium, there's so many different ways to start. But in science, you want to keep things repetitive and reproducible. And this is what guides that. So starting with a single base map, that is map units and features, which are the lines and contacts, should be defined on a single base map. So here's 3 different data sets, for example, of a crater on Mars. Not really important what they are. Different colors mean different things. But the focus is you should define a single base map. And this is where all of your contacts and your features and your unit observations are rooted in, so that if anyone picks up your map, they know what data to compare your observations in for their own uses. And then next, you can have additional data, and these support your base map observations, but they add to it. They're not kind of that tie for everything. Next, you want to do scale-based mapping. So once you have your data set, then your whole map, all of those contacts and lines should be drawn at a set fraction of your publication scale. Now, a publication scale is that map scale that would be printed and put maybe on a wall. So for example, if you have a map scale of 1 to 1 million, a good rule of thumb is to map at a quarter of that size. So 1 to 250,000 is where you would look at the data. So this is our base map, and we're starting to draw those contacts and linear features at our map scale. And this gives a beautiful line fidelity for a map and creates a product that is not too detailed or under detailed for the science you're trying to communicate for a study area. Lastly, we want our map to be rooted in observations. And by splitting geologic observations from interpretations, you create a product that withstands the test of time because the observation should stand no matter how your interpretations might change because your understanding of the body of geologic processes or Mars, how it changes over time. So for example, looking at this data set and kind of this area right here in the center, I'm observing a smooth and flat deposit that kind of has some rounded margins. Maybe it's coming up against some hills and there's some ridges. So from our understanding of what lava flows look like on Earth and how they look different on Mars, I can then interpret that this is a lava flow. And so my observations will always remain the same of the data, but then, the lava flow type or different pieces of the interpretation may change. But collectively, these fundamental principles create maps that are internally consistent, repeatable, and reproducible, which is the goal of any scientific experiment we're doing, and they're objective because there are some inherent limitations that are within geologic maps that we'll talk about. So with these maps, these planetary geologic maps, we have strengths and limitations. Starting with the strengths, data is accessible. Field sites aren't always accessible. Like if you wanted to go map the Sahara Desert, hard to get to. But if you want to map Pluto, data is out there and you can observe the planet and start to make geologic observations of it. The methods are inclusive. One of the key criticisms of field geologic mapping is that you must be able-bodied to be able to hike for many hours across really rugged terrain for really far distances. But if you were to make a geologic map using data, it's all the same geologic principles that you're applying using technology that is accessible. And finally, database maps are innovative. Because you don't have the access to hand-on rock, you have to get creative with how you're representing the geology that you're observing and how you use different data sets to understand a landscape. But with this comes our limitations. So you're restricted by the resolution and coverage of the data. Those flyby satellites sometimes only get tiny pieces of a planetary surface, or you don't have enough coverage, or you don't have enough data, or you have too much data. We have so much data of Mars, and mappers can easily get in the weeds, and there's not actually enough time in the world to be able to observe all the data of your study site on Mars. And finally, when we come into these planetary geologic maps, there are inherent unknowns because we just don't have that hand-on rock observations that you can make to say, I know that this lava flow is a basalt, which is a very specific type of lava flow. On Mars, you can say, we hypothesize it to be a lava flow, likely basalt, but there's no way to know that concrete knowledge of it unless you go there yourself and have the suite of tools to be able to study it. So now that we've talked about planetary geologic maps, how they're made, how you understand landscapes, what is the future of this discipline? The Europa Clipper is going to go to Jupiter's moon Europa. It's going to launch here in October 2024, and it's going to study this icy moon. So different from Earth that has a rocky crust, Europa has an icy crust, and it's going to use a different suite of instruments to observe this satellite, this moon, and we get to see how you would map that using this new type of data and observing this really unique body. Da Vinci and Veritas are going to go to Venus, and these are going to launch in 2028 and 2031, hopefully. And Venus has a really dense, thick atmosphere, so you can't see through it with your naked eye. So they have creative different types of instruments, which means we get to make creative different types of geologic maps to understand Venus. And then lastly, what I'm going to focus on for the rest of this talk is Artemis, which is NASA's suite of missions to return astronauts to the moon. And this is really exciting because we get to leverage the Apollo heritage of astronauts walking on the moon and collecting samples to advance our understanding of the moon. And this is a photo of NASA astronaut Edgar Mitchell, who is actually holding a geologic map to help him as he goes through his traverse on the surface of the moon. And NASA and the USGS made these missions, pre-mission maps, to understand what the site is and where they want to go and send the astronauts to collect samples and photography for the mission. But these maps and this style of maps weren't continued after the Apollo missions ended because there was no need for them to actually continue. So as we move into this modern era of crewed exploration of the moon, these require more advanced maps that meet how technology has changed since the 70s and how we have different types of data, and our understanding of the moon has changed over the decades. So in preparing for this, NASA is encouraging field testing of maps for astronauts. So this is a photo of Kate and Andre, who are NASA astronauts in northern Arizona, where scientists created data-based planetary style geologic maps that were then tested in the field by the astronauts and scientists. So thinking all the way back to those initial slides that I showed you of a field geologist going out and identifying units A and B in contacts, they would go out and test these maps for the accuracy of, for the units A and B and those contacts made from data, are they there in the field? How are they different in the field from those hand-on rock observations from what we're seeing in the data? And in doing so, they hope to iterate these type of maps to ultimately make planetary geologic maps for Artemis that do 4 key things. First, frame science objectives. So for a given landing site on the lunar surface, what is the science that you can do there, and what are your hypotheses? And then for those science hypotheses, identify locations or stations where they can collect data to start to answer those hypotheses, and where would you walk between them, maybe collecting more data. And then once crew is on the actual lunar surface, these maps should help locate the crew, where the crew thinks they are, where planned science sample, either like rock samples or photo samples, should be collected. And then lastly, help navigate the crew, because there are engineering limits and crew safety limits that must be considered. So a map can show, the communication coverage and where dropouts are, or areas of greater than 20-degree slopes that astronauts can't walk on. And so this maximizes both crew safety and mission science. So I encourage y'all to follow the Artemis 3 geology team as they start to make these pre-mission maps. And then as Artemis 3 actually is executed, and then all of the science return and the maps that they give back, and show how our understanding of the moon is advancing through Artemis missions. So with that, I want to thank y'all for watching and thank AGI for having me, and I wish you all the best mapping.
Our next presenter, Dr. Robert Herrick, will talk about the study of low-angle impact events and the unique landforms created by them.
Hi, my name is Robbie Herrick, and I am at the University of Alaska Fairbanks. Today I'm going to be talking about impact craters on the moon and other planetary bodies that have formed from non-vertical or oblique impact. And I'll be discussing some experiments that we've been conducting to try and understand the formation process for these interesting and unusual features that we see on the planets. Before I get into that, though, I want to briefly acknowledge my colleagues that helped me conduct the experiments at the Johns Hopkins Applied Physics Laboratory and the NASA Ames Research Center. So if you look at this first slide here on the left, you see an impact crater that's about 1 kilometer across on the moon. And the bright stuff that you see around the crater is the ejecta. And you'll notice that the ejecta seems to be missing to the left or west of this crater. And the reason for that, as we'll find out shortly, is because this crater formed at a non-vertical or relatively low impact angle, and there's actually ejecta missing in what's known as an uprange forbidden zone. So why in a broader sense should you care about low angle impacts? Well, let me draw your attention to the equation at the top of this page. And what it is telling you is that if you have a population of comets and asteroids striking a planetary body from random directions, then the percentage of impacts that are occurring at less than an angle theta with respect to horizontal is equal to sine squared theta. And so if you do the math, what this is telling you is that on a typical planet, roughly half of the impacts that occur will occur at an angle less than 45 degrees, and a fourth of the impacts that occur will occur at an angle less than 30 degrees. And so it's important to understand the process for forming these low angle impacts, because implicit in using the crater population to determine the age of a planetary surface implies that you have some knowledge of how the crater size depends on impact angle. And also, you would like to know how material gets deposited within and exterior to the crater for a low angle impact, because this will affect the decisions that you make in terms of exploring a lunar crater, or understanding, for instance, the process, the details of the process for how an impact crater might wipe out the dinosaurs. Before I get into low angle impacts, let me briefly show a movie of a vertical impact. And this was taken at the NASA Ames laboratory. And you can see for a vertical impact that what you get is you start with a cavity, and material gets thrown out at a 45-degree impact angle, and then that cavity expands and the crater grows. And then at the end of the process, you end up with a crater that is circular and axisymmetric and has more or less a parabolic shape with a raised rim. And so in the 1970s, there was a famous set of experiments conducted by a couple of scientists with last names Galt and Wittkind at the NASA Ames facility. And they demonstrated how the shape of the crater and the ejecta pattern changed as you decrease the impact angle. And what happens as you go to lower impact angles, first the ejecta starts getting displaced in the downrange direction, which in all of the examples that you see here on this slide are to the right, is downrange. And then as you go to lower impact angles, you start getting the forbidden zone, just like you saw in the title slide here. And this uprange forbidden zone has kind of an outward curving V to it that you can see here. And then as you go to even lower impact angles, then you start getting also a downrange forbidden zone that has sort of straight edge boundaries. And you get kind of a downrange ray that is material that is the impactor, and some ejecta that is ricocheted and gone downrange. In these experiments in the 70s, they also had some limited capability to try and use little dowels and take profiles of the craters and get some of the basic information about the shape of the crater with decreasing angle. First thing that you'll notice here is that the craters get remarkably smaller as you decrease the impact angle. And in fact, the volume of the crater is dependent on the sign of the impact angle. And so this was an important empirical observation that was made with these experiments. As you go to lower and lower impact angles, first in the uprange direction, you get a depressed crater rim relative to the downrange and cross-range directions. And then eventually you also get a depressed downrange rim, so that you get kind of a saddle-shaped crater in the end. And finally, at the lowest impact angles, you get kind of a elongated crater in the downrange direction. And in some of the lower impact angles, the wall, the interior of the wall of the crater is steeper in the uprange direction, so that you get and shallower in the downrange direction. And so this is after this set of experiments in the ensuing 20 years or so. There were some studies done looking at the crater populations on the moon and other planets. And in general, the numbers of craters were sort of what you would predict based on the impact angles observed in the experiments, and the crater forms were more or less what you would predict. What we've been doing in the last decade or so is going back and revisiting both the observations of lunar low angle impacts, craters resulting from oblique impact, and also going back and conducting a new set of experiments. And so if we look at the new data for the moon, we now have much higher resolution imaging, which means we can see a lot more small, fresh craters with well-preserved ejecta blankets, and we can look at the topography of those craters. And so we can compare these lunar craters in much more detail with experiments. And then our experimental capability has also improved over the last few decades, so that we are able to much better capture movies and preserve the impact cratering process. And then after the final crater is formed, we can use structure from motion technology to get a detailed before and after recording of the topography, the shape of the final crater, and the deposition of ejecta. So we can conduct the same experiments, but end up with a whole lot more details of the data. And so one of the things that we want to do with this new data, and both from the moon and from experiments, is try and get some of the details of the excavation process and how do we end up with these unusual crater forms. And you can imagine that while this crater is growing, for the low angle impacts, what changes? Well, it could be maybe this ejecta cavity as it's growing, the curtain is distinctly tilted in some direction. Maybe the growing cavity is no longer circular. Maybe the distribution of material that's getting thrown out of the crater is no longer axisymmetric. So some of these details we didn't have much of a handle on from the initial experiments, and we're hoping to learn more as we go forward. So let me start then by showing you an experiment that we conducted at a few hundred meters per second. And this shows a side view, and this is a relatively small crater. This was done at the Johns Hopkins facility. And that facility allows us to do a lot of experiments at lower velocity, but with a rapid turnaround time. And what you can see here is you'll notice that the ejection angle, even in the forward downrange direction, still seems to be about 45 degrees, just like with the vertical impact. But in the uprange direction, what seems to be occurring is that there's simply a lack of ejecta there. So, another thing that we saw from these experiments, so on the left here is a couple of stills from the experiment I just showed, along with the topography of the final crater developed from the structure from motion here. And then one of the things that we observed in these initial experiments is that if we change the target material from a well-rounded quartz sand, which had relatively low strength, to a basaltic sand with more angular fragments and a wider distribution of grain sizes, so that the target material has a little bit of strength to it, we get a somewhat different shape to the crater and a little bit different distribution of ejecta. And that's going to be, I'm going to show you some of the important differences from the target material here a little bit later on. So one of the things that we found out from just from these low velocity experiments that we conducted was we now think we have a pretty good handle on how you form this kind of outward curving V forbidden zone that you see in some craters. And this is actually a Martian crater, not a lunar crater. But what appears to happen is that you have the ejecta coming out still at 45-degree angles, but you have a missing wedge of ejecta. And for the initial ejection, which is the ejecta that's going furthest from the crater, you have a large wedge. And then as crater excavation proceeds and the ejecta velocities start decreasing, the wedge of that forbidden zone gets smaller and smaller. And so the end product of that is this kind of outward curving wedge here. And these are for craters, but you'll notice the crater is still circular. And these are for craters sort of in the 10 to 15 degrees with respect to horizontal. So, moving on, this shows a whole set of craters that were formed all from a 2-degree impact angle, but from a variety of different impact velocities and into a couple of different target types, both the lava or basalt sand and the quartz sand. And one thing I want you to notice is that to get kind of a really elliptical shape, you need a target with a little bit of strength. But whereas the craters that are in the quartz sand always end up with kind of a teardrop shape. And so we can see both of these types of craters on the moon. So the Messier crater, which formed in the lunar mare, which maybe has a little bit of strength, has this elongated shape that we see in the lava sand, whereas the crater Torricelli, which forms more in sort of highlands, less strength material, has kind of this teardrop shape. So now what I'm going to do is show you a movie from a variety of different, a set of movies from the same shot from a variety of different angles for a crater that produces what we've called sort of an arrowhead or heart-shaped crater. And let's go ahead. And by the way, the two craters on the left are also again from Mars. And the bottom left crater is actually a well-known crater on Mars because it is the crater that formed during the InSight mission and created the largest earthquake that was observed by the InSight mission on Mars, which was a seismometer on the surface of Mars. So I'm going to show you some movies of the crater that forms this crater that you see on the bottom right here. And you can see the ejecta coming out, and you see the uprange forbidden zone that forms as the ejecta is forming. And you see these are laser planes that allow you to see the interior growth of the crater cavity as the ejecta is being deposited. And then we have some side views here. And so from this, we can then go ahead and collect. So on the bottom right is the topography of that crater after it is formed. And then in the upper shots here, you can see a snapshot of the laser plane and how we can use the time sequence to understand how the crater is growing. And so some of the initial results that we get from this is that, as I discussed, it's easier to get an elongated crater, Messier-like, with material, target material that has a little strength to it. And the forbidden zones, in particular uprange, mostly have to do with simply not depositing material in that direction. We have confirmed that the crater mostly forms downrange from the impact point. And we're learning about how the excavation cavity forms and its shape over time. So these are just some observations of ongoing work, and I thank you for your time, and hopefully you enjoyed some of this presentation. Thank you.
Our final presenter, Dr. Brian Day, will speak about how data available through interactive maps on NASA's Solar System Treks portals can be used by many audiences to study extraterrestrial impact craters.
NASA's Solar System Treks is a family of online, browser-based data visualization and analysis portals. They are designed to advance mission planning, planetary science, education, and public engagement. They allow users to view the surfaces of a growing number of worlds as seen through the eyes of many instruments aboard many spacecraft across the solar system. Today we will take a look at NASA's Moon Trek portal. From the home page of NASA's Solar System Treks, click the menu entry for the Moon. We'll fly down to the surface of the Moon. Click the Explore button to launch the Moon Trek portal. The portal opens with an option for a tutorial. We'll skip that for now. As in any GIS system, we can pan and zoom. Here we'll pan to the crater Tycho. One of the first things you might want to know about Tycho is, how big is it? That's actually very simple to determine. We'll open the Tools menu, select Calculate a Distance, and now we'll just draw a line from one side of Tycho to the other. We see that it is about 85 kilometers across. That's a big hole in the ground. We next might want to know, how deep is Tycho? Again, that's as simple as drawing a line. Using the elevation profile, we'll extend the line to either side so we can visualize the rim. And we generate an elevation profile that allows us to easily measure the heights of mountains, the depths of valleys across the surface of the Moon. We also have the ability to generate a bounding box around any terrain we like. We can draw a rectangle around Tycho here, and it gives us an option to generate either an STL or OBJ file to send to our 3D printer to make 3D prints of any terrain that we like. The tools also allow us to draw a path anywhere we want across the surface of the Moon. The tool will then come back to us with a QR code that we can scan into our smartphone, put our smartphone in a pair of cheap Google Cardboard compatible goggles, and fly the path we just drew in virtual reality. Dropping down to the controls in the lower left corner, we can switch from flat map mode to interactive 3D globe and activate game controller mode so that we can use standard keyboard game control keys and our mouse to fly across the moon interactively in 3D. We can drop down into craters and fly over mountains. This is really a lot of fun. While in 3D mode, we can get a better feel for the size and scale of lunar features with the Country Mover tool. This allows us to select any U.S. state or country and drag an outline of that across the surface of the moon for size comparisons. Using the Fly To control in the lower right, we can fly to any location on the moon, either by latitude and longitude or by location name. Here we'll fly to the Marius Hills. The Marius Hills represents one of the most spectacular collections of lunar volcanoes on the moon, but they don't look very spectacular here. Opening up the data menu in the upper left gives us access to thousands of different data layers taken from many different instruments. We can select here a laser altimetry layer that allows us to see the precise ups and downs on the surface of the moon far more easily. This reveals the many cones and domes of the Marius Hills. Now we'll add another data product. We'll select a gravity map from Japan's Kaguya spacecraft. In this view, we'll see areas of high gravity appearing in red and areas of low gravity appearing in blue. For added data layers, we have options to toggle visibility on and off, look at generalized information about the data product, take a look at legend information, inspect detailed metadata about the data product, we can even download the data for use in other tools, and we can remove the data product from our stack. Most interestingly, though, we can adjust transparency of data layers, allowing us to blend different data products. Once you've created a custom visualization, you might want to save or share it. This is easily done by generating a URL. You can copy this, paste it into an email, send it to your colleagues. They'll open up Moontrek, and it will recreate your visualization for them. We'll now use Moontrek to fly down to the south pole of the moon, where sunlight streams in horizontally, creating deep, dark shadows. There are craters at the south pole of the moon whose floors have not seen sunlight in over a billion years. These could be excellent locations for water ice to have accumulated. But piercing these shadows can be difficult. We can change that, however, by switching to a laser altimetry view, allowing us to view the floor of the craters. We can also switch to a color-coded slope map to help us plan traverses. We can overlay this with actual areas of permanent shadow. Loading additional data products allow us to see maps of average temperature, maximum temperature, and here we have a map for hydrogen abundance, an excellent tracer for the possible presence of water ice. Switching to an ice stability at depth map shows us how far we would have to dig down to get to a temperature where ice could remain stable. In permanently shadowed areas, we don't have to dig at all. Ice can remain stable right at the surface. Zooming into the Apollo 11 landing site, we can look down and still see from orbit the descent stage of the lunar lander that took the astronauts down to the surface of the moon. We can also see dark squiggly lines that are the actual footprints of the astronauts on the moon. Next, we'll switch to the base of the Apennine Mountains and the great lava channel of Hadley Rill, which is explored by the Apollo 15 astronauts. The Apollo 17 astronauts landed in Torres Littrow Valley, deeper than the Earth's Grand Canyon. Looking closely, we can see a giant landslide deposit that rolled off the face of South Massif Mountain and covered much of the floor of the valley. Returning to the south pole of the moon, we inspect the incredible terrain that will be the site of exploration by our Artemis astronauts in just a few short years. Conduct your own explorations of the moon and many other planetary bodies using NASA's Solar System Treks at trek.nasa.gov.
Thank you for attending today's Earth Science Week webinar. Immediately following this presentation, the recording will be available on the Earth Science Week playlist of the American Geosciences Institute YouTube channel. Please join us for the rest of the webinars in this series as we continue to celebrate the 2024 Earth Science Week theme, Earth Science Everywhere.